My lecture today is going to be divided into two parts. Part 1, we will talk about the optics of specular microscope, and part 2 will talk about the optics of the operating microscope. Before we start talking about the optics of the specular microscopy, we have to know what is meant by specular reflection first. Specular reflection is a type of reflection or surface reflectance that is always described as a mirror-like reflection of light from the surface. Specular reflection has special characteristics such that the incident light is reflected into a single outgoing direction, and hence the name specular is derived from the Latin word speculum, which means mirror reflection. The angle between the axes of illumination and observation is critical, and the specular reflection is therefore only viewed using one eye. In this slide, we can see the rules of reflection in the first image, where we can see that we have an incident light ray and a reflected light ray, and the normal, which is a line perpendicular to the reflecting surface. In the rules of reflection, the angle of incidence should be equal to the angle of reflection. When we talk about specular reflection, we have a group of incident light rays and a group of reflected light rays. If the group of the incident light rays of the reflected light rays come into one direction and in one plane, we call this a specular reflection. However, if the reflecting surface is a irregular surface, as in this image, the group of the outgoing light rays will go into different directions, as we can see, and this is known as diffuse reflection. Specular microscopy. This technique is used to assess the health of the corneal endothelium, whether in a healthy patient or in a healthy person, or the donor corneal endothelium. In the same way, we can use this technique to assess the lens epithelium and to see if there are zones of discontinuity within the lens using the specular microscopy method, using specular microscopy. And we have two different types for the specular microscopy. We have either the contact or the non-contact specular microscopy. In this technique, the illumination axis and the viewing axis of the slit lamp are symmetrically displaced from the normal line to the cornea, and a narrow illumination beam is used, and usually we get a narrow field, so the patient eye movement becomes a problem with this technique. The slit lamp examination of the endothelium. The steps can be made easy as follows. Set the microscope magnification to a high magnification of 16 times or above and position directly in front of the eye to be examined. Remind the patient to fixate straight ahead. Angle the light source between 45 and 60 degrees to the microscope. Now adjust the slit to a medium width and look into the microscope. Using your joystick, bring the parallelopiped image of the cornea into a sharp focus. Gradually change the angle the illuminating arm makes with the microscope until a bright, dazzling area of the precorneal tear film is seen. This is the image of the dazzling light or the coming from the precorneal tear film, and exactly behind this we can get a clear specular reflection of the corneal endothelium. The contact type of the specular microscopy is composed of an illumination and a viewing path that are placed through the opposite halves of a special microscope objective lens, and the front element touches the cornea and eliminates the eye movement. The advantages of using a contact to a non-contact specular microscopy. Usually the contact microscopy allows higher magnification. Also, it allows video recording and documentation of large overlapping areas with a wider field of examination, and it ensures that the reflection that comes from the interface between the cornea and the contact element does not overlap the image of the endothelium. This is an image for the contact type of the specular microscope and how we can go for a larger field of examination using even video imaging of different areas of the corneal endothelium. The printout that you usually get from the specular microscopy usually consists of an average number, which is known as the cell density, an average number of the corneal endothelial cells. This number is variable according to the age of the patient, with a minimum allowed number of 2,500. Below this number, we will consider that the cell density is below normal, and the average cell size, which is variable also, with an average cell size of around 500 microns, and a maximum and a minimum cell size is also given in the printout with a coefficient of variation in percentage. This coefficient of variation should not exceed 30%, and also the percentage of hexagonality of the cells, which should always exceed 50%. Below 50%, this means that we have a low percentage of the endothelial cells in a hexagonal shape. And accordingly, we can interpret the different printouts of the endothelial cell count. For example, in this printout of specular microscopy, as we can see here, the cell density is reported to be 2,915, so it is within normal. However, the average also cell size is within normal, which is 343, but the maximum and the maximum cell size is 915, which is above normal, and the coefficient of variation is 36%, which is more than 30%. So we have so many cells of different sizes. We have very large cells as well as very small cells, what we call pleomorphism. And at the same time, the percentage of hexagonality is actually, it is more than 50%, it's borderline. This is a normal count, a normal endothelial cell count, but with pleomorphism, as it shows so many cells having different sizes. The second part of our lecture, as I said, will be involved in the optics of the operating microscope. The idea of the operating microscope is that it consists of two compound microscopes that are mounted at 14 degrees of each other. Having these two microscopes mounted with this degree gives us the binocular stereoscopic viewing system of the operating microscope. The compound microscope consists of two optical components and hence the name compound. It is composed of, this is the biconvex objective lens that has a very short focal distance and hence a very high magnification power, and the ocular or the eyepiece, which has a lower magnification power and hence a longer focal distance or focal length. This further magnifies the image and projects the image. The objective lens forms a real image. This is the real image that is formed by the objective lens. Within the body of the microscope, this image acts as an image for the objective lens, which further reflects this image or projects this image to the examiner's eye. The eyepiece, in turn, acts like a simple magnifier to form a large virtual image. If we revise again the components of the operating microscope, we'll find that it is composed of the eyepiece, and then a pair of inverting prisms or poroprisms, and then the magnification changer, which is composed of a Galilean telescope, and then finally the objective lens, which adjusts the working distance of the microscope. First, the eyepiece. The eyepiece is actually carries the optical principle of an astronomical telescope. The astronomical telescope is composed of two positive lenses, the objective, which forms the image of at its focal length, and the eyepiece, which acts like a simple magnifier with which to view the image formed by the objective lens. Its length is equal to the sum of the focal length of the objective and the eyepiece, and it gives an angular magnification which is equal to the focal length of the objective lens divided by the focal length of the eyepiece, and this results in an inverted image. So we need a pair of poroprisms in order to revert the laterally transverse as well as the inverted image in order to get a finally correct erect image. If we revise quickly the optics of the Galilean telescope, we'll find that it is composed of a converging lens, which is a plano-convex or a biconvex lens, serving as an objective lens, and a diverging lens, or a biconcave or a plano-concave lens, serving as the eyepiece. The objective forms a real image, and the image formed by the objective lens is diminished in size and it's upside down of the object which is observed. The distance between the objective and the eyepiece is equal to the algebraic sum of their focal length. The negative eyepiece intercepts the converging rays coming from the objective lens and renders them parallel, and thus forming an infinite virtual magnified image that is erect image. The working distance of the operating microscope is equal to the focal length of the objective lens, and it can be changed either to 150, 175, or 200 millimeters. The magnification is equal to the magnification of the eyepiece, which is 12.5 times, plus the magnification of the Galilean telescopes. So we can get a total magnification that is variable from 6 times to 40 times. There are other accessories related to the operating microscope, like having a beam splitter. This beam splitter lies between the eyepiece tube and the body of the microscope, which splits the light into two directions, the camera and the TV, and the teaching eyepiece. The illumination of the operating microscope is composed of a halogen lamp, which has a better illumination with no thermal effect, and a heat reflector to prevent the infrared and the heat radiation from the lamps of the microscope. We have also two different types of illumination, either the coaxial illumination, which is a uniform defined illumination used for the posterior capsule and the vitreous, and the oblique illumination in order to avoid the cornea reflections from the anterior segment. The delivery system of light inside the operating microscope is a fiber optic delivery system in order to reduce the heat near the microscope and allow for an easier change of bulbs during the surgery. This is a schematic drawing of the operating microscope, which is composed of the eyepiece, and as we said, the eyepiece is like an astronomical telescope that is going to form an inverted magnified image. This image has to be rectified by a pair of poroprisms, then further magnified again by the magnifier changing, which has the optical principle of a Galilean telescope, to finally pass the image through the objective lens. The objective lens here faces the eye of the patient, and there are other structures attached to this operating microscope, which are the illumination system that is composed of the halogen bulbs, and as well as the beam splitter, which splits the illumination into two parts. Part goes to the camera or the TV in order to record the operation, and another part goes to the assistant or the side tube for the assistant to be able to follow up the surgeon and to see the steps of the surgery. Thank you.